about a joint work with Yotanimoto and Michivenner about conformal covariance. And the split property. So this is with Yotanimoto and Benner. So, okay. So the setting we're going to of this talk is the algebraic quantum field theory. So algebraic quantum field theory is an attempt to study quantum field theory using operator algebras. And so I want a theory where one can fit together the quantum world and the relativistic world. So on one end we have non-commutativity, and on the other end we have locality, which means that so events which happen far one from the other, far in the power sense, they have to be independent causally. So actually such kind of model can be described algebraically through the Alcaster axioms, no? So we need to specify which is our spacetime, which in our case we can start, for instance, considering the Minkowski spacetime. Minkowski spacetime, which is this real manifold endowed with the user metric, which is 0.0 minus x, y. This is the Euclidean product of the space coordinate, and x0 is the product of the time coordinate. And so Alcaster axioms are very general axioms, which any quantum field theory is expected to respect. So basic relativistic and quantum assumptions like okay, maybe we have to say before what are regions. So we can consider regions in the space-time, which actually are some bounded causally closed region. Which means that all is equal to its causal closure, we have the causal complement of region X is the set of Y whose Minkowski product is negative for any X in O. We need some regions, we need a symmetry group, which actually is the Poincare group, and we need some von Neumann algebra because we want to associate to any region which has this form von Neumann algebra of, for instance, of observables which we can associate to such region. And so we want that this is satisfies this. Clearly it should be, so those algebra should be bigger as we consider larger regions. So if we have just two regions, we want that algebra should be one independent in the other. So very briefly, one want an action of the Poincare group. So Poincare group should act on the network von Neumann algebras through how? Through a unitary representation of the Poincare group, which goes, and so the action is very natural. So is this one. Plus some positivity of the energy assumption. Plus some positivity of the energy assumption, which is some physical condition, which means that the joint spectrum of translation, so the Poincare group is contained in the forward-like cone of the Minkowski spacetime. And actually, one wants another important property, which is locality, which means that to von Neumann algebra has to commute whenever regions are one in the causal complement of the other. And again, another assumption is the vacuum property. So we want to recognize a vector on the Hilbert space. Clearly, those von Neumann algebra algebra has to be all on the same Hilbert space. So we are going to recognize a vector which is fixed by the full Poincare group, and so this vector is unique up to a phase. And we want a property which means that the theory is not trivial, so H is given. So we want that. So the all von Neumann algebra span of the von Neumann algebra generated by any von Neumann algebra associated to a bounded region as omega as a cyclic vector. Okay, so these are very basic assumptions, and actually one can wonder if the assumptions are sufficient to describe a physical theory. This is, for instance, not true in principle, because one can, for instance, have infinite one-particle degeneracy, which can be eliminated by some compact nuclearity assumptions, or one can wonder if, for instance, mathematically it's very reasonable that the Hilbert space is separable. So actually those are basic assumptions where one can start studying quantum field theory. Actually, we are interested in some particular quantum field theory, which are on just on the 1 plus 1 Minkowski spacetime, so one space at one time, which can be decomposed as a tensor product of two theories on the chirality. So we are on the 1 plus 1 Minkowski spacetime, and we wonder when a theory can be decomposed. So we have, those are prototype of such causally closed region, can be decomposed as a tensor product of two theories, which one is here and one is there. And so we are interested in such kind of models, so in actually models on such lines, but we require that not only Poincare group acts on such net, but the the conformal group. Actually, the conformal group is the group generated by Poincare group, and then we consider dilations, which actually is just dilations of the Minkowski spacetime with some special conformal transformations, which can be indicated by P, for instance, P because they are four conformal transformations, and so we have conformal group, and due to this conformal group, it is allowed to consider these theories online, which actually are some fundamental algebra theory I'm going to describe in a minute, and close it to a circle. So actually what we get is a theory on a circle which has some very analog property to the Alcaster's axioms. Actually are the Alcaster for theory on circles. So actually now our regions would be intervals, and so we have a net starting from intervals to von Neumann algebras, and starting from interval to von Neumann algebras on some Hilbert space, which satisfy isotony, which means that whenever I have two interval algebra should be included. Locality, which means that whenever I have two intervals, I1 and I2, which has no intersection, then the two algebras to commute. And we want clearly an action of the symmetry group, which now is the Möbius group. So we want Möbius covariance, which means a unitary representation of the Möbius group, which which acts covariantly. So and the positivity of the energy. Which means that N0, which is the generator of rotations in this matrix group, so is the rotations generator, has positive spectrum, actually non-negative spectrum. And then we want some vacuum property. So actually we want that there exists a unit up to a phase vector omega in the Hilbert space such that Möbius group. It is fixed by the Möbius group and some cyclicity property. Which means that the fundamental algebras generated by any interval algebras as omega as a silicon separating vector. And now, so we know what is our models. Let me spend a couple of words about property of such models. So as I said, these assumptions are very basic assumptions, but some consequences, very important consequences can be deduced by such property as, for instance, Rich-Rieder property, which means that omega is not only cyclic separating for the algebra generated by any intervals of algebras, but any local algebras as omega as a cyclic separating vector, as a standard vector. And so then we have, for instance, Bisogniano-Wittmann property. Oh, maybe I can say a couple of things on the Möbius group. So the Möbius group is generated by three subgroups, which are rotations, which is just take an element and rotate it I theta z. So if you consider the circle as a complex circle, then we have dilations, which means that you can fix an interval. You take your circle, you fix an interval. You can through the Cayley transform, you can remove one point and open it to the line, and then here using dilations as is expected. So it's like this. It is 0 on the line, so it moves like with minus lambda or with lambda x. And then translations. So translations means that you can choose an interval high, and then again open the circle to the line, and then here apply translation. So x goes in x plus a. This is another subgroup. Those three subgroups generate the Möbius group. And the Bisogniano-Wittmann property says that actually the dilation subgroup is generated by the modular theory of the local algebra. So it means that if you consider interval I, and some other axioms like any local algebras are type 3 one factor, or the fact that whenever you consider two algebras, this is again a factor. When I1 is disjoint by 2. This is again a factor. But what the property we're interested in is the split property. And maybe I can go back here. This split property actually is the property of statistical independence. And it is a property which is stronger than locality. It can be formulated just at Conformal algebra level, and actually is the following. So split. Okay. So our assumptions are: you take two fundamental algebras. So the property can be stated at the level of fundamental algebras. You take two fundamental algebras with a vector, and which is supposed to be cyclic and separated for A, for B, a form the relative commutative. And separating. And then this is called standard inclusion. This one is called standard inclusion. And one is called and split property. Okay, we require even that the fundamental algebra. Okay. And so the split property is the following: says that there exists a type 1 factor. Here is a type 1 factor living between A and B. So F is a type 1 factor, and actually this is equivalent to the fact that there exists, there exists a state P, which is a normal state on the fundamental algebras generated by the smaller one, the commutant of the bigger one, so that such two algebras commute, such that this is normal, such that the restriction to A and to B, and to B prime are faithful. And the state phi splits, which means that phi of xy is phi of x times phi of y. Actually, maybe to something to say this equivalence in our paper, we require that A and B prime is a factor. Which is true for theories on the circle, but actually maybe this is abundant as a condition. And so this is split property. And now, okay, so we can check the split property how looking for a state which restricts faithfully on the two algebras which commute and which has this property. And on a theory of the circle, actually, the split property can be introduced considering two intervals, with one which is compactly contained in the other, and we say that the net A satisfying Möbius covariance is split if A of I1, A of I2 is a split inclusion. This is a split property for Möbius covariant net. And so, the first question is Möbius covariant again? So, the first question is Möbius covariance enough to have split property? Maybe it can be deduced as all the other property. The answer is no, since, for instance, one can consider well, the split property was well described in the paper by Doppler and Longo of 1984 on Vincenzo. So we can write something here. But maybe it was introduced as statistical independence property by Google, maybe, I don't know, in the 70s. and yes, 74. Now, what was I to say? Okay, so actually, the Möbius covariance is not enough to have split property. For instance, one can take a Möbius covariant theory, which is a theory as above, and take this as infinite tensor product with respect to vacuum vector, and this theory is again Möbius covariant, satisfies all the above assumption, but does not split property. It's not split property. For instance, one can see or making that a computation of a canonical type of factor, which is described in the paper by Dobliger, or for instance, considering some compactness condition which is ensured by split property. So there are several ways to see that it's not split, that it does not satisfy split property. But what is interesting is that if we require a stronger covariance, so not only Möbius, even diffeomorphism covariance, I'm going to describe in a minute, this kind of counterexample phase. Actually, we will see that ensuring diffeomorphism covariance, it always solves split property. So what is diffeomorphism covariance? So the diffeomorphism group of S1 is just a group of diffeomorphism of S1 which are orientation preserving. And actually, a unitary we can only have projective unitary representation of the Poincare group, and we say that a net A is conformal when, so we have a net which is described by a net of von Neumann algebras by representations of the Möbius group and the vacuum vector. So such a net is conformal is V if V extends to a projective representation of diffeomorphism, which satisfies some properties. Projective means that goes by diffeomorphism into unitary non-basic space, and which satisfies some covariant property, clearly. So whenever gamma is a diffeomorphism, we want such action, and that whenever gamma is a diffeomorphism acting on some local element, so x belongs to AI, and gamma is an element, a diffeomorphism which is localized in the complement, just to fix pointwise the element of the net. And so what is interesting is that whenever A is a conformal net, the split property holds. And so now let me say a couple of words about the proof. So actually the theorem is the following. So let A be a conformal net then it has split property also. And how can we prove it? So the idea comes from a paper by Friedemagen and yours, which is of 96, of considering such functions. So we can consider these functions. we take an element x, which is in the. Okay, so let me fix a couple of algebras. So let's consider two algebras, IA, two intervals, IA and IB. Such interval has to be far one from the other, so actually not with no common endpoint. Which means some intervals like this. So this is IA and this is IB. So we can consider such inner functionals just on the algebra expand. Okay, this is defined when x is an element of the form EB, but it's clear that it extends to linear combination. Clearly, find linear combination such as. For simplicity, let me write just when we have an element like this, and so we have this inner functional, which is interesting because, okay, let me see, it's well defined first of all as L0 as positive spectrum. And then so L0 can be written this way. It's the fact that the spectrum is just defined by non-negative integers. And so L0 is this way, and what is interesting is the following, is that phi of z of x converges as z goes to 0 to this such because p of 0 is the projection on the vacuum vector. So it's just so we have a product state, which is very natural, which is well defined for any element in the algebraic span of such two interval algebras, and we want to prove actually that this is not only defined here, but from the full fundamental algebra generated by the two. And that's enough to conclude the split property. So that's the idea. How can we do it? How can we do this? In the following way. So here is very important the fact that we have diffeomorphism covariance. And we say why. And the idea is this one. If we can decompose, let me first write linear function. So function is this, no? Omega A r equals 0 rho beta b omega, where rho theta of b is equal to. So here actually is the rotation acting on b. So rho of theta moves b with rotation a little bit. And so we can rewrite this in this way. So the idea is the following, is that we can rewrite r equals 0 as a product of two local elements. So C belongs to some local algebra, D belongs to some local algebra, in such a way that I see, so in such a way that they are in this way. Okay, maybe I can just draw a picture and colors. So this is I C, and this one is ID. And such this way, we can move this is A, we can move C this way and D the other way, and this is becomes clearly, sorry, this is C, omega, A, T plus B. And this becomes clearly a normal function on the polynomial algebra. The problem is that this decomposition, we will see, that will really depends on R, and actually we're not told when R will go to 0. So that's the big problem, and actually the idea started to be the following. So we can show, if this decomposition holds for a fixed R, that this linear functional is, okay, we can consider this as the set of Z is defined the linear function. So if X is an element in the algebraic span, we have that the linear function is defined in the full circle. Okay, this is well defined and is well defined for Z belonging to V1. So when X belongs to the algebraic span of these two algebra, the linear function is defined in the circle. But we know that actually for any circle inside the unit disk, here we have a linear function which is even normal. The problem is that we would like to conclude that in 0, linear function is normal too, by closing the circle here analytically, and then conclude normality in 0. The problem is that clearly this decomposition holds whenever A and B are disjoint, and at some point rotating B will intersect IA. So this is the problem. And actually, in order to overcome to this point, we will need a second decomposition. Which is the following. We can find other two C and D, which has the same localization properties, but here will appear a U of G, which is G is a medius element. And that's enough because actually putting again inside the linear function this new decomposition, here the phi of X of Z will be this way, so C omega A so is like this rho equals W G of B. So now we have the same decomposition. This one moves a little bit G, moves a little bit B, so maybe moves it here, and now we can fill the circle this way. I conclude analyticity in the center of the unit disk. And yes, and to do this decomposition is essential to have conformal covariance. And what time is it?
You got 20 minutes.
And so we have diffeomorphism covariance. So you starting with a projective representation of the diffeomorphism group. Again, I have a stress energy tensor, which actually can be described. So for any function here is a solve. For any function which is a smooth function from the circles to R, I can define such operator which is essentially self-adjoint on the set on the algebraic span Akatin, which is the algebraic span of eigenvector of L0. Okay, just, and this operator is essentially self-adjoint. And Ln gives a representation of the Vilas of algebra. And what is interesting is that in this setting, one can find several representations of the universal covering of the Möbius group. And if you one can start with such operators, which are H, which is 1 over n 0 plus C over 24 n minus 1 over n identity, and plus which is 1 over n and minus n, and a minus which is 1 over n and n. These give a representation, they are generators, for a representation of the universal covering of the Möbius group. And in such representation, we can distinguish translations. And translations are given by the following. So P, which is 1 over 4 and with H minus and plus minus and minus. These actually are translations, okay? And some conjugate group, some conjugate generator, which is 1 over 4n, which is plus and plus and minus, which is just which is I H and the intersection of this on P. Okay, so it's just rotated by pi of P. And now what we want to prove is the following, is that position is that whenever you have two intervals, IC and LD, such two intervals cover the circle, and there exist two families of operator which goes from 0, 1 C and 0, 1 such that R equals 0 is equal to CR dr. And actually was the point was that CR, the norm of CR and the norm of dr are smaller than 1 over R over Q, where Q is some positive number and N is large enough. Actually, N should be that 6 pi over N is smaller than the length of the intersection of the intervals. This is IC, this is IB. Should be smaller than the length than L1 and L2. So, again, we find that the norm of these two operators cannot be controlled anymore whenever r goes to 0, so the both decomposition doesn't hold when we go to 0. And this point, so we want to prove it. So okay, so maybe I can start on the other way. No. So actually what is interesting is that one can consider this formula, which is a formula due to Google, Santoni, and Longo. And see that the operator P is due to Google, Santoni, and Longo. And see that the operator P can be rewritten as the test energy of some function plus some C over n minus 1 over n identity. Can be written in this way. Why is it interesting? Because P is actually something like this: 1 over n, 2 minus z over n minus z over minus n. And actually, if you want to consider this function, you can see that it has many zeros. And so it's many zeros, and on each part it is positive. So actually what one can do is to write P as a sum on some pk, so where pk are actually some P associated to interval k, which goes around the circle, and actually T of P is non-trivial at all, but actually comes from a paper by Werner, which shows that even if these functions, which are the restriction of P to such intervals, are not smooth, but just finite norm 3 or 2, such energy tensor can be anyway evaluated on this such ik. And T of pi becomes a sum of T of pk, and any T of pk is affiliated to such interval, and any one of such pk, or maybe I have to so I can define some T of k, which are actually a T of pk plus this one can be called b, so b over n times identity. Such operators are positive operators. One can show that they are actually non-negative operators. And so now the idea is the following. The idea is that one would like to decompose. Make a larger picture. So we have for the first operator here, decomposition as a product of pieces which are here. Okay. For the first and the third, one can do something analogous to the P tilde operator, and actually it's just that P tilde of k is just the adjoint action of rotation of an angle, not rotation, let me say, u of I pi h to k. So actually it's just a rotation, so it works like this. Color, maybe. and here I have again P. Okay, so I put it as a product of. So actually, those one becomes product of local element, which are localized in such regions, and now we can do this. So if, for instance, A is this interval, so IC, sorry, is this interval. And ID is the other interval. I can do this, so I can take this decomposition, take this operator, and the other operator here. Then I take this one and this one, are the product of such local elements, and then again I take this one and this one in such a way that I can rewrite this one as an operator C1, the one which have local elements. So C1 and D1 are localized here C and here D. C2 and D2 this one. C3 and D3 last one. And actually one can check that D1 commute with C2 as D1 is this and C2 is this one. So I can take all the C this way, all the D the other way. And actually I found something which this one is localized here and the other one is localized there. And so this one is localized in IC and the other one is localized in ID. So actually the interesting is that one can break translations. Oh sorry, this is a 0. Oh, so one can break this rotation in some using translation in some pieces which can have some important localization, some strong localization properties, which allows to obtain some decomposition in using algebras with intersect each other. It's important that they should intersect each other in such a way. So this is how the first decomposition works. Actually, let me say just really a couple of words about the second decomposition. The second decomposition relies on the fact that whenever one consider a Möbius, just a Möbius representation of the Poincare group, oh sorry, the Möbius group, so the Möbius representation is unitary positive in positive energy. We can consider gamma of C, which is the subgroup of fractional linear transformation, which maps the closure of the unit circle inside the unit circle. So I mean that this one is the set of all G, which are fractional linear transformation, which maps D1 inside D1. So take the full circle and actually what is interesting is the following, is that two things are interesting. The fact that any element in gamma of C, so any element gamma belonging to gamma C can be unically written in this way. So gamma can be written as G1 kappa T G2, where G1 is and G2 are Möbius, and kappa is the contraction of the unit circle, so maps Z into Et minus T Z. This is the first fact, and the second fact is that any unitary representation of the Möbius group extends to strongly continuous representation of the closure of gamma C, so this actually which is actually the semigroup, the closure of the semigroup, which is analytic on gamma of C. And this is enough to say that actually one can take some product of okay. So one can write. So what's interesting is that R in such extension R at L0 implements contractions. And actually one can choose G1 and G2 such that H, I, 2, which are the joint section of L0, sorry, on L0 of GI, and then shows that actually H1, H2 is again something going to follow U of G R2 L0 U of G by the fact that it's a semigroup. Okay, this is a semigroup. Actually, taking all this, taking this one this way, one can rewrite all the things R2 L0 as to R2 sum H1 tilde, R2 sum H2 tilde, U of G tilde. So it's just a matter of taking these things and then considering the product. And so, which is the decomposition that we need, zero decomposition that we need. And so this concludes the ideas that are beyond the proof of the split property of a conformal net. We have, I don't know how much time do I have. I have time to say a couple of words.
Yeah, a few more minutes.
Okay, one can build up counterexamples. Counterexamples on two-dimensional theories, because clearly the circle can be counterexamples, and I'm making two. And one can construct counterexamples in this way. So one can start with A as the U1 current. So A is the U1 current net. So it's a particular net such that its representations are just automorphism and they are indexed by a charge Q. Okay, let me say what is a representation just in a moment. So we have the representations where Q and is equal to R. And actually, if you have a net of Conformal algebra, representation rho or sigma is a family of representation. Any one of this is acting on an hyperspace, on the same hyperspace, which can be called sigma, which has some properties of isotony, so of virtual isotony, which means that sigma of sigma, yeah, A1 containing I2, so sigma of A1 needs to be containing sigma of I2, and actually proper restriction, so sigma restricted to the interval I1, so I2 has to be has to restrict to, sorry, let me do it properly. Okay, so compatibility, okay, no, sorry. It's just a matter of compatibility, yeah, which means that whenever I have two intervals, and so such that I1 is contained in I2, so the representation of the larger intervals should restrict the representations to smaller interval in some way. And then covariance. So this first one, and then we have covariance, which means that acting on rho of, sorry, sigma of I has to be sigma of di times u of g for any g in, for instance, universal covering of this. So very natural requirements for representations. And when you have a U1 current, they can be always described to a local automorphism, which means that you can choose an interval I in such a way sigma of a I tilde is contained in a I tilde whenever I tilde contains I. Okay. And so when you have U1 current, one automorphism, which such as endomorphism, we have the sigma automorphisms, and they're indexed by charge Q. So actually we can reconstruct a theory, a two-dimensional theory. Considering tensor product. So we can do this. We can consider this net A tilde, which acts on tensor product I take any rational charge, and I take so the direct sum of any rational charge of the Hilbert spaces in this way, and then we consider this net, so A tilde, which actually acts on this. So A tilde is the one given by the direct sum of sigma q times sigma q. Q is in Q. So Hilbert space, pay attention, the Hilbert space remains separable. So here, Hilbert space remains separable. A acts on, so A times A acts on this net in this way. And then, so local algebras. Local algebras are following. So A tilde of I times I. All such automorphism localized in the interval I is given by so sigma of sorry, here. So these are representations of the net, which is I times I. So we can consider this one. So this way. Okay. Of x times y, such that, and some fields psi q. I'm going to say in a minute what is psi q, psi q, such that x and y belongs to AI, and q is a rational number. Now such psi q takes a vector, psi, it's just a shift operator, so it's just c of q prime plus q. So actually we have sigma with sigma tilde, which is such a representation of the net times A, and we consider local algebras, which are such algebras generated by by x, sigma tilde of x times y, where sigma x and y are in such algebra, and such fields operator, which are naturally the shift operator. What is interesting is that such net A tilde is again diffeomorphism covariance, is another diffeomorphism action, but it doesn't have the split property. And that happens because actually it does not have modular compactness. So the split property has this interesting fact that it sits in the middle, nuclearity and compactness conditions for the net, which actually were born just to give partial interpretation to the net. And actually, so as even a relation with partial interpretation. And actually one can show that if split property holds on a net, then this modular operator, this map associating to any x where, no wait, this is not where this is double form. So we have this one is the modular operator of a wedge region. So we have a net, so we have wedge region, algebra associated to such wedge regions, and we have double con here. And so this map is split property holds, then this map should be compact. And actually what one can see is that this map is not compact for such net, because we can find infinitely many vectors in the image of this map which are orthogonal and so stays away from 0. And so actually this is a very actually is a counterexample in the separable Hilbert space. We first improve it when considering Q is just real. It can be done just a real, taking direct sum of any real Q, which gives an Hilbert space which is not separable and clearly not split, because splitting implies the separability of the Hilbert space. But then we realized that actually can be done given a counterexample on Hilbert space which is separable, violating compactness of some modular map. And actually that's why, I mean, this is split property phase. So I think I can conclude here.
Any questions or comments?
How do you check the conformal diffeomorphism covariance in this model?
So conformal diffeomorphism covariance, it just comes from the fact that you can use any sector diffeomorphism covariance, and so one has to check that it acts properly on fields, the covariance. Yeah, and this comes from the tensoriality of cosine, which is something which can be checked by hand. And is contained maybe in Katsubaki model, maybe long Katsubaki model, tensoriality of cosine. And then one can check that everything works.
Anyone else?